Law of total probability. Let's consider a set of events A1 to AN which are mutually exclusive and exhaustive events. Now, by mutually exclusive means that the intersection in between any of two is empty, and by exhaustive means that the sum of all the probabilities of the events is equal to 1, so they form the total sample space. Now let's consider a different event, event B. So the probability of event B is going to be given by the intersection of B with all the elements of the set of events A1 to AN. If I draw here one event, the probability of that event is going to be given by this intersection with all the different elements of the set A1 to AN. So that's a particular way that we can use to compute the probability of an event if we have this set of mutually exclusive and exhaustive events. Let's look into an example. So imagine that we have 3 bags, each containing 100 marbles. So bag 1 has 75 red and 25 blue marbles. Bag 2 has 60 red and 40 blue marbles, and bag 3 has 45 red and 55 blue marbles. So we are going to choose one of the bags at random, and then from that bag we are going to pick up one marble. So we want to look into the probability that the chosen marble is red. Let's imagine that this is our total sample space. We have bag 1, bag 2 and bag 3, and each one of the bags has blue and red marbles. So event red in our case is going to be given by this. This is going to be event B, and we are going to look to the probability of event B. Let's first analyze what's the meaning of bag 1 having 75 red and 25 blue. The probability of having a red, given that we are in bag 1, so bag 1 is equal to 0.75. In the second line we have bag 2, so the probability of being red, given that we choose bag 2, is equal to 0.60. And finally we have the probability of being red, given that we choose bag 3, is equal to 0.45. Now, choosing the bag is a random process, so the probability of choosing bag 1 is equal to 1/3. Now we want to find the probability of choosing red in our experiment. So the probability of red, given that the bag 1, bag 2 and bag 3 events are exclusive and exhaustive events, is going to be given by the probability of red intersection B1 plus the probability of red intersection B2 plus the probability of red intersection B3. And we can write these intersections in terms of conditional probabilities as the probability of being red, given that we choose bag 1, multiplied by the probability of B1 plus the probability of being red, given that we choose bag 2, multiplied by the probability of bag 2 plus the probability of choosing red, given that we select bag 3, multiplied by the probability of bag 3. So we just have to replace the values. So we have the probability of choosing red, given that we choose bag 1, is 0.75 multiplied by 1/3 plus 0.60 multiplied by 1/3 plus 0.45 multiplied by 1/3, and that will give us the total, which is equal to 0.6. The bias rule. Consider two events A and B, such as the probability of A is different from 0 and the probability of his complement is different from 0, and also the probability of B is different from 0. Now, by the definition of conditional probability, we can set up that the probability of A given B is equal to the probability of the intersection divided by the probability of B. And also, swapping B for A, we have the probability of B given A is equal to the probability of the intersection divided by the probability of A. Now we know that the probability of the intersection is commutative, so we can say probability of A intersection B is equal to the probability of B intersection A. So with that, we can write that the probability of A given B is equal to the probability of the intersection. But I'm going to use the probability of the intersection as the probability of B given A multiplied by the probability of A. So that's it, the probability of B given A multiplied by the probability of A, and then divided by the probability of B. Now this is considered the Bayes rule. We can also rewrite this a little bit in terms of the law of total probability, and we can use that law to rewrite the probability of B. So the probability of A given B is equal to the probability of B given A multiplied by the probability of A, and we can express the probability of B using the law of total probability. So we have that the probability of B given A multiplied by the probability of A, which is the intersection, plus the probability of B given A complement multiplied by the probability of A complement. So remember, this is the probability of the intersection of B with A, and this is the probability of the intersection of B with A complement. So this is a second alternative for Bayes' rule. To finalize, let me go back to the previous example, in which we have 3 bags of marbles, each one containing blue and red marbles. Remember, for each one of the bags we have the proportion of red and blue marbles, so we can have the conditional probabilities for the red, given that is in bag 1, bag 2, and bag 3. Also remember that bag 1 and bag 2 and bag 3 are chosen randomly, so the probability of choosing one of those bags is 1/3. Now the question is, if the chosen marble is red, what is the probability that bag 1 was chosen? To solve this question, we are going to use the Bayes rule. So the question is, what is the probability of bag 1 was chosen given that the marble selected was red? So this is equal to the conditional probability of red given that we choose bag 1 multiplied by the probability of bag 1 and divided by the probability of red. So we have all the values, so we can replace, and the probability of selecting red given that is from bag 1 is 0.75 multiplied by the probability of choosing bag 1, which is 1/3, and divided by the probability of choosing red that we have from previous example, that was 0.6. So the final result is 5/12. That's the probability of bag 1 choosing given that the selected one was red.